there's another option for a buffer problem. What's the one equation in this unit? Our friend Henderson-Hasselbalch. And yes, you can use that here too, assuming that you check the assumption and it's OK. Most people will prefer to do this because it is a bit easier. So you weren't given, though, the pKa in this problem. You were given the Ka. So pretty easy to calculate. Minus log of the Ka is the pKa. So you can calculate that, put that in. You have your concentrations, and it should be concentrations. But you may notice that if you actually had moles, the volume would cancel here. So here are the concentrations. But with the same volume, the volume term does cancel. It makes this a little faster, and it gives the same answer, which is great. To use Henderson-Hasselbalch, you also need the 5% rule to be true, because Henderson-Hasselbalch is assuming that x is small. It's assuming that the initial concentrations and the concentrations after equilibrium are about the same. So we can check the assumption. We can back calculate the hydronium ion concentration, which would be x, and see if it's small. We already know it is, so it's OK. So there are two options for buffer problems. But do not use the Henderson-Hasselbalch equation when it isn't in the buffering region. It doesn't hold then. So again, you check the assumption. And if it's OK, it's fine. If not, you need to use option 1, and you need to use the quadratic equation. All right. So buffering region. Now we're at the special kind of problem in the buffering region, the half equivalence point. So here you've added half the number of moles of the strong base to convert half the moles of the weak acid to its conjugate. So at this point, the concentration of HA equals the concentration of A minus. Equal number of moles in the same volume. Those are equal. You can use Henderson-Hasselbalch here and find that if they're equal, you're talking about minus log of 1. So the pH is going to equal the pKa.